We did N, C, Q, Q is P and 1. Even in and then
Okay, display, right?
to the X. So parentheses and the X outside. And then times Q to the
Hey.
Hi, I just got my access code to get into the computer. I had to wait until Friday afternoon to get it so I can get my homework done.
Okay. First of all, yes, I can fix whatever you need to. Okay. Second of all, there's a temporary access code that you could have gotten on day one.
I did get it on day one. I used that one.
Okay.
But then it kicked me out, and I went and I bought the new one.
Okay. I will fix it.
Okay.
All right. But I would have liked to have known earlier. Okay. So then we could have called customer service and gotten you back in. Okay. Because I don't want you to go, a week without doing stuff because of the computer. All right. So I can fix whatever I need to fix. All right. But I would really have liked to have known about it about a week ago. All right. So that we could have got it fixed sooner.
Yeah, she
All right.
did get out, but I haven't heard anything yet. So I assume
Can I retake that first test that we took?
Yep.
Okay, I would like to do that too, and I don't know.
Okay, you'll need to set up time, and my office hours are right now Tuesday, Thursday from 10 to 3, and Monday, Wednesday from 12:30 to 2:30. Okay,
I have.
now that information's on Blackboard, okay? And so if you can send me an email and let me know what time works for you, that's any time. Now, I want you to retake it, okay, but I want to make sure that you know the stuff before you retake it.
The thing that
Okay.
I was really mostly confused on was the dotted graphs. That's what I need to go over that whole
Okay,
part, and I will go over that before I take it.
okay,
Everything else seemed to, like, it was okay. I didn't do my best on it, but
Okay.
the main part that I was confused on is the graph and then the skewed. But
Yep. Okay, all right, so just let me know, send me an email, and let me know what time would work for you, okay?
Then this one we're doing
Yeah.
in 3 days. And I emailed him. He's like, oh, no. They reiterated that I said go over the examples on every week. I'm like, what, everything's due Wednesday, and we don't get it until Monday morning.
This is his equation, and they do it every week.
That's that?
This is the way I do it. I think it's pretty easy.
okay.
How?
Yeah, this is better. Yeah.
Yep, and that much. 4 and then.
So it's actually.
All right, so here's our calendar of events. Note that we're on June the 11th right now. So that means we're dealing with homework set number 7. Now, as it turns out, I did have a couple of people who either emailed me or texted me or whatever else to ask me if there were, certain problems they had on the thing, right? My instincts tell me that's not enough, okay? When I hear from 2, maybe 3 people out of a class of 30, all right, then I'm thinking there might be some other people that have some questions, but I'm not hearing from them, okay? And what I want to do is hear from them, okay? What I do not want, this is my thing I don't want. I don't want you to feel like that if you have a question that somehow I'm too busy, or I have too many other things going on, or my life is meaningful in some other way that I don't want to hear from you. I want to hear from you anytime and every time you get stuck. All right? If you get stuck and it's relatively urgent, you can text me, you can send me pictures of your calculator, you can do whatever. If you need to call me and talk to me, call me. That's my job, right? I'm supposed to be here helping you with stuff. And if you want to send me an email, I do have the thing where I get the email relatively quickly. I might not answer it right away, might not get to it, but my feeling is that there were more questions out there and they did not get addressed. And so then I want to do that. Number 2, these due dates are flexible, okay? If you didn't get everything done, I can change the due date, I can change your score, I can make everybody get 100% all the time, but that's not the point. The point is I want you to learn how to do the stuff. And if you don't know how to do the stuff, I can fix it and make it so that it works. But the time to ask the question is right when you have the question. That's the best option for me because then I can help you at the time when you're looking at it and you're struggling with it, okay? What's going to happen right now is we're going to go over everything. We're always going to go over everything all the time. And if you don't understand how to do it, we can work with that. If you need for me to, revise your due date or something, I can do that. That's not a problem. That's not an issue. But I would prefer to know about the problem as soon as it happens. If you wait and say, well, we'll just talk about it during class, okay, that's true. But I'd rather have you learn earlier so that you come to class and you say, okay, yeah, we did address that. I do know how to do that thing. Because this is going to keep going. We're going to do new material today. I don't want you to fall behind. I don't want you to have to keep working on old material while you're learning new stuff. I want you to get things verified and confirmed as soon as possible. And I am very appreciative of anybody who asks me a question at any time. I want that. I like that. I don't have other agenda items that are more important to me during the week that I have to say, oh, well, I don't want to answer those people's questions. I do want to. I want to. So with all that in mind, we're hopefully going to go through this homework set number 7 on discrete probability distributions, figure out whatever needs to be figured out, and then we're going to move on to the next chapter. And the next chapter is going to take us a couple of periods, and then it'll be time for us to review and then go to the second exam. All right, so what we're dealing with is the concept of the binomial probability distribution. Well, first, we're not doing that one, we're doing the discrete one, right? Well, no, it's the second time. So we're doing binomial probability distribution. That's what we're dealing with in homework set number 7. And just as a matter of review, okay, if I talk about how to do something during class, and then you go to your homework set and you say, how am I supposed to do this? You should look at your notes about how we did it in class in order to know how to do that next thing, all right? If you look at the textbook, or if you look at the hints from the homework, that might not be exactly what we went over in the class. What I prefer is that you do it the way that we talked about doing it in class. The textbook has different things. They go through things sometimes in more detail than what I want you to have to worry about. So if I say we're going to do binomial probability distribution, and I ask the question, what's the formula for that? This is what you should have. And this is what you should do. All right, so you need to know this formula, and you need to use this. It is possible for you to write this down right now. What I want for you to do is to look in your notes and see if you already wrote it down. If you look in your notes and you see that you already wrote it down, well, you really don't have to write it down again, because this we already did. And so if you can find it and you can say, this is what we're doing right now, this is review, okay? So this is what you need to have. So then let's just say that we have a problem. If I say if little p is equal to 0.4, n is equal to 7, x is equal to 3, find p of 3. All right? This would then be a problem that I would have for you to do. This would be like one of the homework problems, right? So I'm going to give you a minute and see if you can make this thing happen. All right? Going through what we did last time, using these numbers, putting them into this formula that I gave you right here to get this answer. All right? And if you don't know how to make this happen, all right, then we need to talk about exactly what's missing here. Okay? So if you look at the previous example and you look at where the numbers go, make this happen. Right? I'll give you a minute or two, see if that'll work.
Oh, yeah.
Yes.
How do I find that C?
Second. So if you put in like this, this would be 7C3, right?
Right.
7.
Oh, I've been hitting that. Okay.
Oh, okay, all right. Oh, Kathleen is here. There we go.
We're not getting paid for that.
Sure. Okay, so D, 3, 7, 3.
What is it? The club? Oh, yeah. Yeah, so the club doesn't have money. That's the way I understood it. So why can't we just like our money on
Yeah, I wrote down the equation for the next
All right, so what I'm hoping is you got 0.2903. Okay. In order to make that happen, you would have to put these things into your calculator that look like this. Okay. So if you don't know how to put these things in your calculator, then that's something we need to fix. As it turns out, Kathleen is here. Kathleen has the mathematical superpower of helping people. So there we go. And so then when we look at this and we say, where is that? This is on your calculator. Where is it on your calculator? I went through it last time. If we need to go through it again, we'll do it again. You need to know what buttons to push in order to get 7C3. But you don't have to get it. You don't have to know what that number is. You can just put it into your calculator. 3 multiply here, right? And then this to that power, and multiply here, and then just hit equals. You don't have to write anything down other than this. Right here. Question.
Usually you just go 3 after the next one, right? Or at least in the homework, like you said before.
Yeah.
What's the MCR key again on the calculators, Rick?
It depends on your calculator.
Yeah, I
I have to look at it. And I have to know this one. It's all right. So what needs to happen is that you need to know how to push the buttons on your calculator to get this thing, 7C3. And then you need to know what buttons to push on your calculator to get this thing to this power, and this thing to that power, and multiply in between. Once you know that, you don't have to write anything else down. You just do this and get the answer. Okay. Now, if you look for the examples on the homework, then the people in the textbook have a much more complicated way of doing this problem. You should not do it that way. You should do it this way. It's a lot easier. Makes a lot more sense. Less buttons to push. There's no need for you to know how to find 7C3. If you already have it on your calculator, you can make that work, okay? And as I talked about last time, 7C3 is counting how many different options we have. How many ways can we get 3 successes out of 7 tries, okay? So this is the first thing, to know how to do this, to know how to get this answer, all right? So then, anybody have any question about how to get these numbers, where these numbers come from? And you should get 0.2903. All right, any question about that?
Can you repeat what NCX accounts? How many what?
It counts how many ways to get 3 successes out of 7 tries.
What does it answer you for? What does it mean here?
Okay, well, yes, thank you. That's a good question. So then, when we're saying, what are we actually doing with this? First of all, get the number. That's the first thing. Get the number. Second thing, let's try to understand what the number is about, okay? So what we're saying then here is, I am looking at 7 people, or whatever, and I want to find out 3 of them that are in a particular category. And what I'm asking is, what are the chances, just by chance, that 3 of these people are in a category, given that the general probability is 40%? Okay, now it's usually easier to understand that process if you actually are talking about specific categories, and we'll do that in just a minute. But what we're going to get to then, this is the probability of a random chance of getting 4 successes out of 7 tries. All right, so let's see what that looks like in actual terms. And I'll do it for this one, and then I'll change the problem for another one. So let's say that I've got, and I just keep going back to these similar examples. Let's say I'm talking about students in music club. Okay, and I know there are 7. There are 7 students in this music club. So that's the entire club, the 7 students. That's the number of observations. N is equal to 7. And I have to have given to me then the general probability of, let's say, having an older sibling. I have to be given that general probability, and in this case, I'm going to say that it's 40%. So that's telling me 40% of the students in this school have an older sibling. So then I'm looking at the students in the music club. There are 7 of them. And I know that this is true. This is a category percent. How many, what's the chance of being in this category? And then I'm asking the question, what is probability of having 4 students with an older sibling in the music club? So I'm looking at the music club. I have 7 of them. Oh, sorry. E. Yep, thank you. Sorry, it's 3. X is 3. So when I say What am I looking for? I'm looking for the chance, just random chance. What is the random chance that 3 of these students will have an older sibling? 3 out of the 7. So then x is equal to 3. How do I describe this variable x? X is the number of successes, the number of people which are in the category, number of people who are the probability of 40%. So this probability, P, is the probability of success. And then X is the number of successes out of N, or from the 7 that I'm looking for. All right. And again, what we're saying is, I know the general probability, 40%. And so I'm looking at this and I'm going to say, it's possible, certainly, 29% chance. That's not a surprise if it happens. So I'd be looking at this and I would be saying, oh, well, I walk into the music club and I say, hey, how many of you have older siblings? 3 of them raise their hand. I'm not surprised. 29% chance of that kind of thing happening. So then that would be one of the numbers that I would think about using. But then if I ask the more general question, which is what you asked last time, Natasha, if I'm looking at the more general question, how many students will I expect to have older siblings? I would need to know all of these probabilities. I would need to look through and see, where am I going to have probabilities that are less than 5%? That would be a surprise. If it's not, then it's not a surprise. So if I look at, for example, 0, and I say, what would happen if I ask the question, what is the probability that I walk in the classroom and say, hey, do you have an older sibling? What's the chance of it being nobody? Well, that's a low probability thing. It's less than 5%. So I would be surprised if I walk in there and none of them have older siblings. Okay? So that's what we're working on. We're working on trying to figure out what to expect. We want to know what's going to happen when I walk into this room. What would be a surprising result? What would not be a surprise? And right now, 3 students saying yes, I would expect that could happen. 0, I'd be somewhat surprised that happens. So then if I walk in there and say, anybody got older siblings? None of them. I'm like, oh, something's going on here. What is this? The only child music club or whatever? All right. Now, as we go through this then, let's do another problem similar to this, okay? And I'll just change the setup, but it's a similar kind of a problem. So, let's say here. The general probability of cat ownership is 30%. What is the probability that out of 25 students, only 4 Okay, so let's see if you can make this happen. Okay, so let's go here. Okay, so let's go to this.
I just took this all the
Three, 4, 5, 6, 7, 8, 9, 10, 11, 12, All right, so if you haven't checked with other people, I want you to check with other people now. Make sure they've got the same numbers you do or similar problems.
Yeah.
All right, Jackie, you got a number?
0.057.
0.057. How'd you get that number?
I plugged in.
Okay, what did you use for N, X, and P?
N is 25, P I use 0.30, X I use 4, and Q I use 0.7.
Yep, that's right. And so when you put that into the formula, you should come up with the probability of getting 4 students would be 0.057. All right. So, Jackie, what does that actually mean?
The probability is going to be 4 people, 25 people, 4 people out of 25 have guessed.
Okay, this is the probability.
Only 4 of the people out of the 25
That's right.
having a cat is 0.5.
0.05. That's right.
Okay,
Okay, team effort, but yes.
we got it.
All right.
You're confusing me, to be honest.
Yeah, okay, well, let's not do that anymore. Okay, no more confusion. All right, what does that mean? How useful is that information to us?
Well, I mean, I love cats, so it's pretty useful. I'm just kidding. I
Mm.
really, I mean, I don't know.
Okay, Emily, can you tell me? Since you're right next to her, I figured.
It's fine, because now you know the probability that only 4 people will have a cat.
Not quite, no. What are we after? What are we trying to find out? What do we want to know? Whether it's usual or unusual, okay?
Sure.
So, yes, the fact is, that's what you want to know when you get down to the end of the situation. You want to be able to say, is this usual or unusual? Because the purpose of statistics would be what? Someone answered me that question. What's the purpose of statistics?
Yes, data-driven decision.
Okay, data-driven decisions, and specifically in this situation,
Understanding things that you're not sure about.
that's good, yes. But it's also true that we want humility, yes, we do. But, yes, we need experience to know what that word means, yes. But what to expect? Usual and unusual are part of these data-driven decisions, okay? The purpose of statistics is so that we're able to make data-driven decisions. And specifically, what does that mean? Data-driven decisions means that we have an idea of what to expect, what is usual, what is unusual, and so then we can decide what to do based on the information of knowing what to expect. So, for example, if I am going to try to sell catnip to 25 students, but only 4 of them own a cat, am I surprised? The correct answer is kinda. All right, because is this less than 5%? It's not. But it's awful close to 5% now, ain't it? So then when we say, is it 5%? It's not. It's almost 6%. But when somebody asks you a question, were you surprised by this? You would say, maybe kinda surprised because it's a low probability thing. It's almost 5%. So it's kind of surprising that I would only have 4 students who would have a cat. Okay, so if you're going to try to sell catnip to students and you brought 10 packages and you're only got 4 students to sell to, that's kind of a surprise. That's what you want to know. If I want to do something and I want to make it happen in some kind of application, I want to know how many people out of this 25 I can expect. 4 would be a bit surprising. because it's close to being 5%. Okay? Now, if that doesn't resonate with you, if that doesn't make a whole lot of sense, well, it might later. If you're able to get this number 0.057, that's good. That's really what I want you to do right now. But eventually, I want you to understand what that actually means. And to be able to say, it's the chance that I have 4 people out of the 25 with cat ownership, that's good as well. But ultimately, what we want to get to is, what does this matter? Why would you have to figure this out? Because it's telling you what to expect. So then when you walk into the operating room, or you walk into the kindergarten, or you walk into the classroom, or wherever it is, you know something about what to expect because you understand how this stuff works. Okay, now let's ask this question. How many of you have a cat in your house? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and I counted 22 students. 11 out of 22. Okay, and Kathleen, no, you didn't count. So there we go. So then I look at this. This is a representation of the table. All right, this is based on cat ownership of 30%. This is my table. Based on my table, I want to know what are the unusual values of cat ownership. Okay, so I've changed my stuff here. I'm looking at this. And now I'm going to use not the formula. I'm not using the formula right now. I'm looking at the table. From this table. What are the unusual values of X? All right. I would like to know this answer. Alicia Bell, can you tell me? 13 and down? Actually, that's not correct. Lisa Peterson, can you tell me?
11, no, just kidding. No,
What a kidder.
11 and down,
11 on down.
yeah, and then 3 and up.
3 and up. Okay, so this would be from 0 to 3 and from 11 to 22. Actually, I don't have the rest of them. Okay, and how did you know that?
Because they're less than 5%.
Okay, because the probabilities are less than 5%. And so we say those would be unusual values of X for me to see. Okay. Natasha, do you have a question? Okay. All right. So then if I'm looking at this, and this is based on n equals 22 and p is equal to 0.3. N is equal to 22 and p is equal to 0.3. So I just took a survey and I just found that 11 students have a cat in the house. Am I surprised? I just took a survey. I asked people to raise their hands. I had 11 people who raised their hands. Am I surprised that I had 11 people raise their hands?
Yes.
Why am I surprised, Shanann, that I had 11 people raise their hands?
That's the majority of
No. All right. Eric?
It's the unusual value, yeah.
Okay. All right. It's in the unusual value category.
What is that?
The number 11. Okay. 11 out of the 22 said yes. So that's the number of successes, the number of people who said yes. That's what X is. X is telling you how many people are going to say yes. And then the probabilities are telling you how likely is that to happen. I had 11 people who said yes. I'm surprised because that was one of the unusual values.
But if you didn't have that chart, it could possibly happen, because it'd be 30%. The chances of,
No.
I don't understand.
Okay, when we're saying 30%, what we're saying is that this is the general probability. This is the general probability that any one person has cats. Okay, it's 30% chance that this person does, 30% that that person does. Okay, when I get all these people together, what do I expect to happen? This is what I expect. I don't necessarily expect 8 people or 9 or 5. There's different possible answers that I could have. How many students own cats? These are all the different things that could happen. The 30% is just for each individual person. But what I want to do is consider the group all together.
Kind of like he worked the formula 22 times, 23 times.
Yeah, these numbers.
Probability of 0, probability of 1, probability of 2, etc.
So
Yeah.
that formula, the binomial one,
Yes.
23 different
Yep.
times.
Yeah, if I did this formula 23 different times, I'd come up with all these. We didn't have to because I gave you the table.
Yay.
Right. So what's going to happen on the test?
You're gonna give us the table?
I'm going to give you the table for one question.
Are you gonna give us that, formula too?
I'm going to give you the formula too for a different question. Okay, these are 2 different questions. I'm going to give you the formulas all the time. I'm going to give you the table. What I need for you to do is to show me that you understand what that is telling you, okay? Specifically, if I gave you the formula and I tell you the situation, you would put the numbers into the formula, get the answer, and say this is that probability. If I ask you this question, from the table, what are the unusual values of X? You look at the table, you see the ones that have probability less than 5%, and you write down this answer. From 0 to 3, from 11 to 22. Now, what does that mean, really? What that really means is, if I have 11 people who say they own cats, that's a surprise. That's more than what I thought it was going to be. So that's telling me that something is unusual. If I came to this classroom and I wanted to sell cat things to you, and it was 11 people, I'd be like, wow, I did not expect that. I didn't expect that many people to be owning cats because I thought the general probability was only 30%. So is this the cat loving statistics class? Okay. Well, not necessarily maybe liking. If it were the loving ones, you'd be way out there. Okay, but this is a class that owns more cats than I expected them to have. So that's telling me that something's going on. That's what we're trying to figure out. All right. Any more questions about these 2 kinds of problems? We've got the formula problem, and then we have the table problem. Okay, those are 2 kinds. All right? Question?
I just have a question about the general probability.
Yes.
When these are all subject to that
Yes.
number, right?
The general probability has to be given to you in the first place. Yeah, that's right. And in about 3 weeks, we'll say, well, how would you do this if you didn't know that? But we're not going to do that
so
right
your
now.
question for the table would be what are the unusual values?
That's correct.
So notice that's a big P, capital P, and over there, the one you put in the formula is lowercase, so really pay attention.
Yep, that's important. All right, so now we're going to ask 150 people about their cat ownership. So I asked 150 people about cat ownership. And I want to use the empirical rule to find unusual results.
This is the same.
Okay, so what does the empirical rule require us to know? We need the standard deviation and the mean. Okay, so then what you're going to look for is, if I know that I've got 150 people and the general probability of cat ownership is 30%, how do I find the mean and standard deviation? If you are here, you should have it written down in your notes. You look at those notes and find out. I'm sorry, what? June the 6th. I don't know exactly which class it is. Taylor, can you tell me the formula for the mean and standard deviation?
N times P times Q, which would be 150 times 0.30 times 0.70.
No, not quite. Okay, formula for the mean. Donna, you got the formula for the mean?
Oh, what?
Yeah, you do, actually. You got the
150 times 0.30.
Okay, so in general, the formula is n times p. Okay, it's not n times p times q, it's just n times p. Right, Taylor? Is that think about it?
I thought you said standard deviation.
Oh, okay, so can you tell me the formula for standard deviation?
It is N times P.
No.
Square.
It's the square root of n times p. There. It was after we got done talking about everything else. We talked about this. This is the last thing we talked about last class. Question?
So I know you said that on test we're gonna get the formulas.
Yes.
Are we gonna be told which type of standard deviation to use since we have two standard deviations?
If you're given a binomial problem like this one, which I just gave you, then it's this standard deviation kind of a thing.
How do you
So
know
we'll
if
just be
I
able to
know?
recognize it.
Yes, you will. Because it'll be just like this. I asked this many people about a thing. The general probability is this much. Use the empirical rule to find unusual values. And you'll say, oh, which formula is that? You look at the formula list. Binomial probability distribution, mean, this. Standard deviation, that.
Are all of the standard deviations for this test the binomial?
No, we did last time before that time, okay, we did standard deviation for just the discrete probability distribution. So that would be a different one where I would give you a list of different probabilities and a list of different numbers. Okay. And we are, of course, going to have a practice test so that you'll be able to look at it and you'll be able to say, this is what the problem looks like and this is what that formula is. All right, check with your neighbors, see what your neighbors have going on, see if they have the right answer. The right thing. All right, Amanda, you got numbers for me here? Well, I guess that's a helpful number. That's the standard deviation, but what I want to know is, what are my unusual results and how would I find them? That's what I really want to know. Okay, yes, standard deviation is 5.61. But that's not the final answer of what I want. Nikki, what do you got for me?
Below 33.78 and above 56.225.
I'm asking 150 people, so no, it's not like that.
Yeah, I wrote down all these notes, but I didn't understand how you got the answer. I see you got 48 to 72 in the notes, but I don't know what it is.
Okay, so the first question we need to say is, what does the empirical rule say?
The 5% and 95.
Okay, so where are the 95% for the empirical rule?
That's what I don't understand. How do you find that?
Okay, what does the empirical rule say about the 95% of the data? Al, can you tell me? Okay, Amber, can you tell me where the 95% of the data are according to the empirical rule? I want to know what the empirical rule says about 95%. Taylor.
Is it between 71.2 and 48.8?
It could be, but I want to know what the empirical rule says. What is the actual statement of the
95%
empirical
of the
rule?
time.
Okay, not quite there, Taylor. What is it? 95% of the data is where? According to the empirical rule. The general statement.
It's between -2, 5 and 95. I don't know.
Okay, Ally's saying what?
It's between the mean minus 2 standard deviations and mean plus 2 standard deviations.
Okay, 95% of the data is between the mean minus 2 times the standard deviation and the mean plus 2 times the standard deviation. Okay, that's the general statement of the empirical rule.
Okay.
All right, Taylor, does that make sense? Okay, it's probably what you did,
Give
right?
us a couple minutes to figure it out.
Okay,
Now that we know that much.
sure. So, what did I say, 150? Yeah.
Oh, that's right.
That's wrong. If you get a negative number.
The mean is 45.
Yep.
Minus
2 times 5.61.
31.5, right? That's 2 times 31.5.
No. When we say the mean minus 2 standard deviations, you have to multiply first before you subtract.
Right, so what was standard deviation?
Standard deviation is 5.612.
Oh, yeah, I got that.
Okay.
So how did you get that?
Okay. N is 150. P is 0.3. Q is 0.7. Multiply those together, and then take the square root.
Oh, it's great.
Okay.
Thank you.
All right. So, and this is really a good thing for you to understand. If you get to a point where you're getting a negative number in this situation, then that doesn't make sense. Probably something wrong with what you're doing, okay? And that happens every once in a while when you do that. It's also true that it's possible that you could get a negative number, and that tells you that it's not bell-shaped. Okay, remember the empirical rule works for bell-shaped data. If it's not bell-shaped, maybe the empirical doesn't work. So that's another option that could happen. So getting a negative number when you're not supposed to is like a red flag. Okay, something's going on, right? So, Eric, what'd you get?
For the 95% of the data, it's between 56 and 50.
Okay, usually we'd say it the other way around, between 33.8 and 56.2, right? Between the bottom and the top, like that. Okay? So 33.8 and 56.2. I'm sorry, I just said it to myself and I forgot it. 33.8, 56.2. 56.2, right?
Yes.
Okay. All right. But that's maybe not the best answer, because we're talking about numbers of people, aren't we? So 34 and 56 would seem to be maybe a more reasonable answer. It's not a huge thing, but can't have parts of people generally, right? So what would be then the unusual results? We still haven't got that yet.
0 to 34 and 56 to 150.
Yeah, so it would be below 34 or above 56. Okay? Okay, so now you're not walking into a classroom, you're looking at a group of people, 150. So let's say it's all of the business majors or something. You say, okay, I'm going to market my catnip to all the business majors. How many do I expect to be cat owners? Out of the 150, somewhere between 34 and 56. If it was less than 34, I'd be surprised. If it's more than 56, I'll be surprised. So this is telling me what to expect out of this great big number of people. How many of them do I expect to be cat owners? And the answer is not 45. That would be the average. But that's not the results that I would expect. I would expect anything from 34 to 56. This is why we have to use probability, because we don't know how many people own cats. And so then when we walk into the situation, we're not thinking that we exactly know the answer. We're thinking a range of possibilities. So that we could have somewhere between 34 and 56. We should probably be prepared for that. And if we want to be super, we'd even prepare for other possibilities because we just don't know what's going to happen. Because we don't. All right. And we don't even know that 30 is correct.
So was I wrong when I thought that you had to do the order operations in times 2 by the standard deviation first? And then minus the, because I came up with different numbers. I did 2 times 5.612.
That would be about 11 point.
It was 13.224.
No, it's not. If I take 5.612 and I multiply that by 2.
Oh, yeah, that, but then plus the 45.
So then I would take 45 plus that. And I would also take 45 minus that. So if I do 45 plus that, I get 56.2.
Yeah, sorry, I don't know what I did.
Okay.
I don't know what I did.
Now, specifically, when we say that the order of operations is important here, your calculator does know that in this situation. So if you just type 45 plus 2 times 5.612 equals, your calculator knows the order of operations. It will give you the correct answer. If you hit the equal sign too quickly, if you say 45 plus 2 equals, that's not what you want. Don't want to do that. Not want to hit equal sign right away. If you put in the entire thing and hit equals, the calculator will do the order of operations for you. It is also possible for you to multiply this, write that down, and then do the adding and subtracting, but you really don't have to do it that way. You could just write this down and then just do it on your calculator and get the answer. You don't have to write down the intermediate steps. Your calculator knows how to do this. So you need to be able to understand and communicate correctly with your calculator to make that happen. So what we're looking at now are 3 different kinds of binomial distribution problems. The first one where you just use the formula, put in the right things, get the answer. The second one where you're looking at a table and you're finding unusual values based on that. And this third one, when you have a large sample, then you're able to use this using the empirical rule to find out what the unusual results will be. So those are the 3 kinds of binomial distribution problems, and that's what you'll have all these formulas on the test when you do it. All right, so now it's time for our break. So we'll go to 4:13. Come back and do the new stuff.